These are your Chapter 9 Notes 3 on sampling distributions of a sample proportion. So we're going to talk a little bit about what we did the other day in class where we're working with a sample proportion and a sampling distribution. First of all, sampling distribution, just to recap, a distribution is another word for a graph. So we're dealing with a graph that shows information about samples. A sampling distribution is a graph that shows all possible samples of the same size from a population. The graphs that we've been working with on the sideboard in class, those are examples of the beginnings of sampling distributions. Variability is another word for spread. So if I ask you about a sampling distribution, a distribution is a graph. If I talk about variability, I'm talking about the spread of the sampling distribution, the spread of the graph. And what we mentioned yesterday was that the spread of the sampling distribution is affected by the sample size. Not by the population. The bigger the sample we take, the less spread out your graph is. The smaller your sample size is, the more spread out. So we have an inverse relationship. The larger n is, the less variability the graph has. Now, in regards to describing the sampling distribution, when we describe a sampling distribution, we're talking about SOX again, shape, outlier, center, and spread. We're going to be focusing this time on shape, center, and spread, and not on outliers. We had said yesterday that the shape of the distribution is approximately normal if two things are true. N times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. This was our rule of thumb that we had talked about yesterday, rule of thumb 2. Some people also use the claim that, or if n is large, again, if n is a large number, even if your probability is small, that should ensure that you get a number that's bigger than or equal to 10. The center of our graph, we're going to use the mean, which we'll call mean mu sub p hat, and that's equal to p. And for standard deviation, we'll talk about standard deviation. Since we're dealing with approximately normal data, hopefully, we use our center as our mean and our standard deviation as mu sub p hat, which is equal to the square root of p times 1 minus p, all divided by n, if the population is at least 10 times the sample size. Otherwise, we're not allowed to use this formula, and we really don't have another formula that we can use at this point. We have some questions at the bottom of the page dealing with a presidential candidate who's running for office. It's reported that the candidate nationally has the support of 38% of Americans. Polling company takes a survey of 1,000 Michigan residents and finds that 42% of them support this candidate. Find P. Well, we got to find P in number 1 and P hat in number 2, so let's talk about the difference. The P that we're working with in problem 1 is an example of a parameter. This is the population proportion. Whereas P hat is a statistic, which is dealing with the proportion of our sample. So these are both going to be percentages, and we do have two percentages that are listed in our introduction to our problem. We have this 38% right here, and we also have this 42%. So which one is which? Nationally has the support of 38% of all Americans, so this sounds like a parameter. It's dealing with the entire population. That's what we're going to use for P in this problem. We have a survey of 1,000 Michigan residents. That's not everybody in Michigan, obviously, so that's going to be our statistic and our sample proportion, which is 42%. To calculate sigma sub p hat, we're going to use our formula that we addressed in our spread description, which is the square root of p times 1 minus p over n. In this problem, we're using p, which is 0.38, and we're going to calculate 0.38 times 1 minus that, which is 0.62, all divided by n, which is 1,000. Again, if you're calculating this on your calculator, what I might suggest doing is kind of the following. First of all, we're going to do a little square root right here. So let me slide this over. We're going to do square root. I like doing 0.38. I know 1 minus 0.38 is 0.62, so I'm just going to type it in like that. And then you can divide by 1,000. And what's nice about typing it in this way is you only have the one set of parentheses you're worrying about. Here's your standard deviation. I am not going to round this value at this point, just in case I have to do some probability calculations a little bit later on. 0.015349267. In problem 4, can we legally use this formula in our sample? Well, we are allowed to use this formula if the population is at least 10 times the sample size. And in our problem, our sample size is 1,000 Michigan residents. So if the sample is 1,000 Michigan residents, the population is all Michigan residents. So as long as we have at least 10 times this number of people living in Michigan, we're good. Now, I don't know exactly what the population of Michigan is, but I know it's more than 10,000. So we're good here. And we're going to say, yes, the population, and I'm going to be specific about who I'm talking about here. I'm not just going to say the population is at least 10 times the sample size. That sounds like you're kind of just winging it. We're going to talk about who the population is. The population of all Michigan residents. So if our sample is 1,000 Michigan residents, the population is all Michigan residents, is at least 10 times the sample size, 10 times 1,000, which equals 10,000. So I'm going to address who the population is, what this population actually is, and that it's actually bigger than 10 times the sample size. Can we use a normal approximation to describe the sampling distribution? Well, if that's the case, we said that n times p and n times 1 minus p both have to be greater than or equal to 10. I'm feeling pretty confident here. Our sample size is 1,000, which is already pretty big, and if we multiply it by 0.38, you'll notice that we get 380. That is greater than or equal to 10, and we're in pretty good shape. If I do n times 1 minus p, same kind of idea. We get 1,000 times 1 minus this. If you just want to write 0.62, which is what it's equal to, that's fine. When you multiply that out, you'll get 620. That's also greater than or equal to 10. Both values work, so our answer is yes. In number 6, we're doing a probability calculation. This is sort of our step 1 of our 5 steps, and in our second step, we're going to calculate z. We're going to take our value 0.42 and we're going to subtract the mean of the p-hats. The mean of the p-hats is this value, this 0.38. And you might recall that it's 0.38 because the mean of the p-hats is equal to p. And we've already said p is equal to 0.38. Our standard deviation of p-hat is this big decimal value we calculated back in step 3, 0.015349267. Can you round this value? I say no, because at this point we aren't done with the problem yet. I'm fine with you rounding at the very last step of a problem, but don't round before that. So let's use all the decimal places we can to ensure that we've got a little bit more of an accurate answer. On your calculator, when you crunch this out, I would probably suggest putting your numerator in a set of parentheses if you're doing this all at once. And then what I would do is divide it by this square root that we came up with, this 0.015 number. I'm just going to retype it because I already see it kind of on the top of my screen. When I do this, I get 2.6059. We're going to round that to 2.61. Our step 3, we're going to find the probability that z is greater than 2.61. And you can use either your table for this, or we can use our normal CDF command. Because we're going to the right, we're just looking at the region from 2.61 to 99. Which is 0.0045. I think I've got a little bit of room where I can squeeze my little graph in here. 3 tick marks each side. We're shading from 2.61, which is over here to the right. That should be a pretty small region, which seems to correspond with what we got. In our final question, it says, if we increase the sample size to 4,000 Michigan residents, find a new value for sigma sub p hat using our formula. So going back to our problem from number 3, this time we're going to do the square root of 0.38 times 1 minus that, or again, you can write 0.62. And we're going to divide this by 4,000. So again, I'm going to do 0.38 times 1 minus that, which is 0.62. We're going to divide this by 4,000 this time. And when we crunch this out, you get 0.00767 with some other decimal places. Now, once we're done with this, it says describe how you could get the same answer using a different approach. We had mentioned yesterday that if you change the sample size, the standard deviation is going to be affected. In our problem, we originally started with a sample size of 1,000, which you'll see up here. Now our sample size is 4,000. What have we done to our sample size? We've multiplied it by 4. So since we've multiplied our sample size by 4, remember in our standard deviation formula, if this number changes to like a 4, if we kind of multiply it by a factor of 4, square rooting the 4 has the same effect as multiplying your standard deviation by a half. So that's what happens here. How could you get the same answer using a different approach? Let's take our old standard deviation by 1/2. We're going to take half of 0.015349267, and when you do that, what you'll notice is that you get the same answer that we came up with using our other method. If you take half of 0.015349267, there's your 0.00767 number. Two ways of getting the same answer using different approaches.